And so yeah, so without further ado, let's welcome Mario, and he'll begin with our first lecture. So thanks, Mario.
Okay, so thanks everyone for coming, and thank you, Jeff, for this nice initiative of the reading seminar. Today is going to be a bit different than other days because it's going to be kind of an overview of some aspects of the book, and then in the following sessions I will go more into some details. So I hope this first lecture is not too anti-pedagogical, but we'll see. so so let me start with something very basic and classical, which is talking about some aspects of Ricci flow. So Ricci flow was introduced by Hamilton in 1982, and it's a natural evolution equation for a metric on a manifold. So this is the equation. We have a one parameter family of metrics, and then the variation of the metric in time, and which is asymmetric to tensor, has to be -2 times the Ricci tensor of the metric. So this is a very natural evolution equation because essentially the Ricci tensor is the unique symmetric tensor that can be cooked up out of the metric, which in a way that only depends on second derivatives of the metric, and is invariant under diffeomorphisms. So it's a natural tensor. And this is the usual Ricci tensor cookup out of contraction via the metric of the Riemann curvature tensor. Okay, so if we choose local harmonic coordinates at some given time, then the Ricci flow takes a very simple form, which is the following. So the partial with respect to t of the components of the metric, these are functions on the manifold, okay, local functions on the manifold. This is the Laplacian of Gij plus some expression which depends on the metric itself and first partial derivatives. So here, a warning is that I'm using, for the Laplacian, I'm using the analysis convention. So this is going to be, my Laplacian of functions is going to be minus the Hodge Laplacian on functions, okay? So this is you can think of it also as the Laplace Beltrami operator on functions, which is written this way. And as I said, this Q is some lower order quadratic expression in G and its partial derivatives. So why this evolution equation is useful? Well, because it may allow us to put some canonical geometry on our manifold. So the first step in this program is to see whether solutions exist. So this is classical theorem by Hamilton and the Turk, which states that if you have a compact Riemannian manifold, G0 is the metric, then the Ricci flow has a unique solution for some time 0t with t positive with initial condition G0. Okay, so at least we can start flowing a given metric, and if our flow is good, it's going to converge to some nice geometry. So what is the effect of Ricci flow on the metric, on the form, or on the shape of our manifold? Well, as I said, the Ricci flow can be written like this in harmonic coordinates, and this is a heat type equation for the components of the metric. So similarly as when you have some body, which is a heat, when you put some heat in a given time, then as time flows, the heat, the body tends to cool down, and the heat becomes, or the temperature becomes uniform with time. So the Ricci flow has the same effect on curvature. So it makes curvature homogeneous along the manifold when t goes to plus infinity. Okay, so this is just a picture of a solution of the heat equation on an interval. Okay, so this is not quite true, and this is one of the most interesting aspects of Ricci flow, because in different regions of the manifold, depending on the initial metric, your metric may evolve to very different constant curvature models. So this ends up causing some tension, which may end up breaking your manifold into pieces. So this, if this works and does at least in dimension 3, then one can maybe detect the topology of the manifold that you have. So this is the picture, the usual picture for the composition into the composition by spheres of a 3 manifold. And this previous picture is one of these diagrams for the formation of singularities under Ricci flow. Okay, so this is a beautiful idea that was posed by Hamilton in his papers, and then it was used by Perelman later to solve the geometricity conjecture by Thurston for 3 manifolds. And one of the nice and striking aspects of Perelman work is that he brings in ideas from physics, in particular from statistical physics and the theory of 2-dimensional sigma models. So this is something that in the community of geometric analysis is not so well known, but is there. So I took the liberty of taking this a small picture from a lecture by Pavel Severa, who is going to play his work is going to play a role in this first lecture. Okay, so what is this? This is all about the introduction. So what is generalized Ricci flow? So generalized Ricci flow is now a generalization of this classical equation in a more general setup where you have some new ingredients, in particular a closed free form on a manifold. And this generalization is motivated by the theory of 2-dimensional sigma models in physics. So Ricci flow will appear as a particular case. Okay, so let me go into some details. So we fixed a manifold M and a cohomology class in this manifold. I'm going to assume that M is compact for simplicity. One could think of more general cases. Then generalized Ricci flow is defined for a 1-parameter family of pairs, GT, which is a Riemannian metric as before, and BT, which is a 2-form. And the flow is given by this pair of equations. Okay, so now you see the first sum on the right-hand side of the first equation is just the Ricci tensor for the metric varying in time. And now we have add to this natural symmetric tensor the another symmetric tensor given by half of h squared. What is this? So h squared is essentially the symmetric tensor that you hook out of 2 copies of h and contractions with the metric. So in coordinates, h squared ij is given by this expression here. Okay. Okay. So this so far so good. We have just the form the Hamilton's equation for Ricci flow by adding the symmetric tensor, which depends on a 3-form. So I didn't say, but H is a family of closed 3-forms, which is hooked up out of the given representative of the cohomology class H0 by adding the differential of the 2-form depending on time. Okay, so what about the evolution equation for the 2-form? Well, for the 2-form, what we have is that the partial derivative with respect to t needs to be minus d star. The d star here is the adjoint for the L2 metric with respect to the the adjoint of the zero differential with respect to the L2 metric of the 3-form. So this lowers one index. So this lowers one degree of the form. So this is a 2-form, and this equation makes sense here. Okay. So in components or in coordinates, if you want, you can write it like this. So if you take a frame which is orthonormal with respect to the given metric, then you can write down d star h as minus sum of nabla ei contracted with h. This is the Leibniz beta connection, and then contracted with the ij. EI, sorry. Yep. Okay, so this is the questions we are going to consider. So let me go a little bit into the motivation for these equations. So as I said, the the equations appear in the theory of two-dimensional sigma models in physics. So let me say a few words about this to give an idea. Okay, so a two-dimensional sigma model is a physical theory where the fields are given by maps from a surface into a manifold. Okay, in order to construct the Lagrangian of the theory, which is going to tell us what are the critical solutions by extremizing, we need to fix some background geometry. So we fix a manifold, we fix a metric, and we fix a 2-4. So given a field, which is a map from sigma into M, sigma is a surface, then the Lagrangian can be written as follows. So S phi is the L2 energy, so the energy of the differential of the map. If you want, just the L2 normative differential of the map, plus the integral of the pullback of the 2-4. So now I have to think of critical points for this functional as some sort of trajectories for a one-dimensional object, which physicists call or think of as a string. Okay. So let me make an analogy which may clarify this picture. So the analogy is with the magnetic geodesics on a manifold endowed with a 1-4. So if you fix a Riemannian manifold, then and you fix a 1-4 on this manifold, this magnetic geodesics describes the motion of a point particle in the presence of a magnetic field, which is going to be given by the exterior differential of the 1-4. And the Lagrangian, whose critical points are these magnetic geodesics, is given by this functional. It's just the L2 norm of the length given by the norm squared of the derivative of along the curve, and plus the pullback of the 1-4 to the interval of definition of the curve. So this is a perfect. There is a good analogy between these two pictures. So this will be like the picture for point particles, and this is like the picture for strings. Okay. So what has to do this thing with our flow? So in order to quantize this physical theory, this sigma model, physicists introduce some machinery called the normalization group flow. So the normalization group flow is an evolution equation on the coupling constants of the theory, which you have to think of as anything which appears in the Lagrangian multiplying either components of your fields or its derivatives. So in this case, the coupling constants, if we go to the Lagrangian, the coupling constants are going to be given by the metric and the 2-4. Okay. So they introduced this normalization group flow to keep track of the change of the scale, and this is the actual flow. So this is it's exactly the generalized Ricci flow that I mentioned before. Okay, for the metric and the 2-4, it's exactly the same expression. So one of the nice things, or I don't know, striking things of this physical picture is that physicists need to introduce a new ingredient, which is neither the metric nor the 2-4, is a function on the manifold in order to make sense of this normalization. And this is a function they call the dilaton field. It's like a new field, an auxiliary field in the theory, and it must satisfy its own evolution equation. So this is what physicists tell us that the dilaton should evolve by. So this equation, which is minus the scalar curvature plus 1/12 of the norm square of h, minus 2 Laplacian of it plus norm square of the gradient. And even though this is the equation considered by physicists, we will see that this is not quite the equation that the analysis likes. I will go back to that in a few lectures. Okay, so what are the stationary solutions of the flow? So the metrics and two-form solving this thing but constant in time. Well, they are supposed to be closely related to conformal field theories, two-dimensional conformal field theories. And by some complicated procedure, physicists show that there is some nice energy functional, which is this string effective action, which I'm writing here, which precisely captures these critical points. Okay, so what is this functional? Well, you may recognize that what I have here in the integrand is precisely the evolution equation for this dilaton field up to a minus. And then we have this weighted volume form by the Riemannian volume form and the dilaton field. E to the minus FTBG is the right volume to consider. And quite surprisingly, for me at least, when you integrate by parts, what you get is precisely Perlman's energy functional for Ricci flow that he used to keep track of the formation of singularities in his work on Ricci flow about three manifolds. Okay, so these are the physical ingredients which lead to the definition of the flow. So now let me go into the mathematics. So are there any questions so far?
Can I ask a question?
I hope everyone feels free to go ahead and ask whatever questions you want.
Yeah, Francis, yeah.
I was just wondering, how does this new action relate to the one that was called S?
Yeah. So this is the action for the sigma model. So it means that it's an action for a function, a smooth map from the surface into M. Okay. And what physicists say is that in the quantization of the sigma model, up to doing some perturbative expansion, etc., then this is the evolution equation that keeps track of the change of scale for the coupling constants. And I'm not quite sure about how do they write down this string effective action out of that, but this is supposed to capture, I mean, at least in the string theory, it's supposed to capture like the low energy theory coming from your string theory.
So it's supposed to be equal to S in some regime or something?
No, but this is not. I mean, this is an integral on the manifold M on the target,
Oh,
and the other one is an integral over, you integrate over sigma, and it's a function for the maps from the surface into the manifold. So I don't think there is a very precise mathematical procedure for how you get this energy functional, this string effective action out of this. But
it's like the ones that are kind of fixed by the renormalization group satisfy that they're critical.
Yeah. So this functional is going to give you as so the gradient flow for this functional is going to be essentially this generalized Ricci flow.
Oh, okay, thanks.
Okay. So I don't know if this is more than a device, but the physicists interpreted this as like critical points, as so these like stationary solutions as giving rise to some supergravity theory in the target, which is like the low energy regime for the string theory. Yeah, I don't know if this answers your question.
Okay, thanks.
Anyway. more people is asking something. Someone asked something in the chat.
Oh, I'm sorry. It's not a real question. Never mind.
Okay, so I go. Okay, so anyway, so as for the math, so many of the things I said maybe I'm completely unfamiliar to you, so it doesn't matter. This was more like motivation and another thing. But so beyond this physical motivation, what one can expect about this generalized Ricci flow as for the mathematics is to provide some fruitful tool for other classification problems in geometry, in topology in higher dimensions. So, for example, there is a nice proposal by Jeff Streets about how an adaptation of generalized Ricci flow to the case of complex manifolds may be able to say something about the geometrization of complex surfaces and the classification of complex surfaces. Okay, so naively, why we may expect that is because this generalized Ricci flow is more flexible than Ricci flow that has been useful for the understanding of three manifolds. And this is just because we have extra parameters. So of course, this is more flexible. There is no doubt about it. But can we actually use it to find some canonical geometries in a broader class of manifolds than the ones dictated by Ricci flow? Okay, so let me give you an example of that. So why this flow may be useful in finding canonical geometry. So let me illustrate it with a simple situation, which is to consider stationary points for the flow. Okay, I'm going to compare stationary points for the flow, for the generalized Ricci flow, and for the Ricci flow. So for Ricci flow, stationary points are given by Ricci flat metrics. So they are in particularly Einstein. So by this classical theorem by Ricci, which is a special case of the well-known Hitchin-Thorpe inequality, if we have a compact four-dimensional smooth manifold which admits an Einstein metric, then the Euler characteristic of the manifold must be bigger or equal than zero. It must be non-negative. And furthermore, if the Euler characteristic is zero, then this happens if and only if G is flat. Okay, so take M equals to S3 cross S1, a very simple compact four-dimensional manifold. Then the Euler characteristic is zero, and therefore M does not admit any Einstein metrics, because otherwise this would give you that G must be flat, and by the Killing-Hoff theorem, we'll have the universal cover must be R4. Okay, so S3 cross S1 does not admit any Ricci flat metrics. So let us look now at the case for the generalized Ricci flow. So what are the stationary points of the generalized Ricci flow? These are given by solutions to these equations, where H is some closed three form on your manifold. Okay, so this has slightly more freedom. So let me make two interesting comments. The first one is that this equation corresponds to the vanishing of Ricci tensor for a metric connection, which is not the Levi-Civita connection. It's a different connection, which has a skew symmetric torsion, and is given by this formula. So here, nabla is Levi-Civita, okay? And here you take the three form, rise one index. Oh, I have a problem with my computer, and I'm going to shut down in 1 minute, I think. Jesus.
Do you want to send me your slides? I can keep talking. Oh, geez. Okay, so yeah, the whole thing didn't crash, I guess. It's just him. And then, yeah, maybe to answer your question, Josh, while we're waiting, yeah, I mean, this F is more like energy, but yeah, I mean, I think, yeah, I think the difference between energy and entropy is always a little fuzzy anyways, but people usually think of entropy as more sort of localizable. But on the other hand, the F functional is also localizable because it admits this arbitrary parameter F, little f, which you sort of use to get local information on the manifold anyways. But let's see. So yeah, maybe I just say again, since a bunch of people came in, maybe I think after I announced, but maybe I don't know everyone here. We could introduce ourselves perhaps while we're waiting, but maybe send me an email. I guess a lot of you I do know, but
Back, Jeff.
please, okay, yeah. I just
Sorry
want to
about
say
that.
again, please go ahead and send me an email if you're showing up, and I'll keep you on the list. Even though the one Zoom link will work for every meeting. But okay, yeah. I filled the time as best I could. So.
Thanks. Yeah. Okay. I hope this doesn't happen again. I don't know. Anyway, sorry about that.
Sure.
You need to allow me to share.
Yeah. Just a moment. There should be good.
Yeah. Okay. Sorry for that. Let me go back to the place where I was, which is here. Okay, so recall that I was trying to compare Ricci flow with generalized Ricci flow to see that this.
Wait, I don't see your screen. Did you?
Oh, I tried to. Okay, now.
Maybe it's just me.
Do you see it now?
Yep.
Okay, thanks. Sorry. So I was trying to compare Ricci flow with generalized Ricci flow to see that these give us some more freedom. And then the first thing was to analyze like stationary points for the flow. So recall that what I said is that S3 cross S1 does not admit any Ricci plat metric by the Hitchin-Thorpe inequality. So now if we go to the case of generalized Ricci flow, then stationary points are given by these equations for the Ricci tensor of a metric, and it's a closed free form on the manifold. So in particular, the H is going to be harmonic with respect to the metric, okay? Taking D in the second equation. Now, these equations correspond to the vanishing of the Ricci tensor for a metric connection, which is and this one. It has totally skew symmetric torsion, and it is given by taking Levitz beta connection and then writing these other expressions. So maybe I just, let me do something. Oh, here I can do it. Yeah. Do you see the whiteboard, right?
Yep.
Yeah. What I mean is that nabla plus xy is given by Levitz beta xy, so x and y are vector fields in the manifold, plus 1/2 g minus 1 of h xy Okay, so here I'm contracting x and y with the 3 form. I get a 1 form, and then I use the isomorphism from the tangent to the cotangent bundle given by the metric, which I invert, okay, to cook up this expression. So this gives me a natural connection with total skew symmetric torsion, which in this case is furthermore closed. Okay, let me go back to my slides. Good. So the other comment, which is maybe more enlightening, more geometric, is the following. So here, this h squared is a semi-positive tensor. Okay, so recall that h squared is given in components. H squared, sorry, is given in components by the following expression. I M H J L N. Okay, and this is semi-positive. So what this means geometrically is that if I think of this expression here, I may allow for solutions on manifolds which have some positive curvature. Okay, so setting this first equation to 0 allows me for some positive sectional curvature maybe on my manifold. Okay, so let me go now. Let's take this as a hint in our example of S3 cross S1 and try to solve these generalized Ricci flow equations, or in the stationary case, this equation here on the S3 cross S1 manifold. So yep. So recall that the equations are the same as the Ricci for this Laplace connection equals to 0. So if we take M to be S3 cross S1, which is the same as, or is diffeomorphic to SU2 cross U1, so I'm going to regard this as a group manifold. Then I consider generators for the Lie algebra of SU2 cross U1, E1, 2, 3. So these 3 first generators are going to be generators for the SU2 Lie algebra, and then E4 is the generator of the U1. And in terms of the dual frame, I have that the differential is given by this expression. dE1 is E2, 3, dE2 is E3, 1, dE3 is E1, 2, and dE4 is 0. So here E super ij is the wedge. And recall, let me go again to the whiteboard, 1 minute, just to recall that if you have if my EIs are left invariant vector fields on my manifold M, which is a group, then if I take the dual frame, which is given by one forms which are also left invariant, and this is left invariant, then the differential acting on EI xy is going to be, well, let me write it in terms of the basis, which is better. The EI, EJ, EK is minus EI bracket EJ, EK. Okay, so this is a very basic thing, but just to recall you that the exterior differential for left invariant forms can be completely cooked up out of the Lie bracket on the Lie algebra. Okay. So let me go back to the slides and discuss this example. So I have this Lie algebra this is the dual frame, and these are the relations. And now take H to be minus C1 to 3. And using these relations, you can see very easily that this is a closed free form. Actually, this is just the pullback to SU2 cross U1 of the Cartan free form on the Lie algebra U2. This is being variant and closed, as I said. Now I have actual being variant metric on the manifold, which is just the diagonal metric in this basis. And then just by its form is the and thing which I have not tell you, but I will hopefully next day. This metric and this free form are such that nabla plus is flat. So in particular is Ricci flat, and therefore we are solving this equation. Okay. And this is something very general about compact Lie groups, about simple compact Lie groups. Okay, so there is a general result tells you that this geometry should have a solution to these equations. Okay, so far so good. We have seen that at least at the level of the stationary points, generalized Ricci flow is more flexible, it's more powerful than Ricci flow. It has more stationary solutions. So what about actual solutions of the flow? What about non-constant solutions of generalized Ricci flow? So there is this theorem by Jeff Streets in 2008, which says that generalized Ricci flow has short-time existence. So say that you have a manifold M, you fix an initial remaining metric G0 and initial closed free form. Then the generalized Ricci flow has a unique solution in some interval 0t for t bigger than 0 with initial condition G0 H0. So here I'm taking B0 equals to 0. Okay, so I'm writing this in terms of the free form instead of the associated two forms. Okay. So let me say something about the proof, because some ingredients will appear later. So for the proof, what you do is to implement the so-called the torque trick. So you consider a gauge fixed version of the flow for the metric and the free form. So we're going to, instead of taking the evolution equation for the two form, we're going to take the corresponding evolution equation for the free form. So it means that we take D in this expression and exchange the partial T with the D. So we get partial T dB. This is going to be dH, the free form, and then this is minus dd star H, which in my notation is going to be the Laplacian of H. Okay. So I have this gauge fixed version, which involves not only the metric and the free form, but also a one parameter family of vector fields. So I modify the first evolution equation by the Lie derivative of the metric with respect to X, this vector field. And the second equation, which is obtained by taking D in this expression, by the Lie derivative of the free form with respect to the vector field. So what is this vector field? This is not a random vector field. It's very special. What you do is to take G minus of the trace of the difference between the Leibniz beta connection at time t and the Leibniz beta connection at time G0. So the initial Leibniz beta connection. So recall that the difference between the two, let me write this in the whiteboard. So what is this vector field? So recall that we have an initial metric G0, and then we have a one parameter family of metrics GT. And then recall that the space of connections in the tangent bundle is modeled on the one force with values in the endomorphisms of the tangent bundle. So it means that if I take nabla GT minus nabla G0, this is a one form on the manifold with values in the endomorphisms of the tangent bundle. And now I can take trace. If I take trace of the endomorphism, what I get is a 1 form on the manifold M. And if I raise, let me call this sigma t, if I raise the index, or if I apply this duality between tangent and cotangent directions given by the metric, then G minus 1 GT is my vector field. Okay, so G here is regarded as something from the tangent to the cotangent on the manifold. Okay, so this is the so-called the third trick. Okay, so with this choice for gauge fixing, it turns out that the equations are parabolic, and this ensures short time existence for this system of equations, which is not the original one. And now what you have to do is to engage. So it means that you pull back everything by the one parameter family of diffeomorphisms to get an original solution of this equation and the corresponding equation for the free form. And using that, you get the two form potential by direct integration in this expression. So partial dB is equal to minus the star h. Okay, so this is just the application of the okay, so this is the way you prove short time existence. Are there any questions about this part?
Sorry, Mario, could you repeat how have you obtained the gauge fixed equations from the original ones? I mean,
yeah, the way you get the gauge fixing is essentially by declaring your let me write it. Yeah. So the principle for obtaining the gauge fixing is the following. So the principle is that GT HT is a solution of partial T GT equals -2 Ricci plus half h squared, and partial T GT equals minus T star h. This is a solution of this system if and only if the following G tilde T H tilde T defined by the pullback by the one parameter family of diffeomorphism integrating the vector field xt. And this thing and this thing, this other metric and freeform solve the gauge fixed system.
okay, thank you.
Can I ask?
This is the way you. Yep.
Why is this new system easier to solve?
Well, the problem with the initial. Let me go back to my slides. The problem with the original system is that when you linearize it, is not parabolic, meaning that what you find on the right hand side of the evolution equation is not going to be I don't know what is the correct name is. I mean, it's not going to be. It's going to be elliptic, but not. It's not going to be. It's not
Strictly
going to be
or
yeah,
strong.
strictly. Yeah, strongly elliptic, which is what you need to find the short time existence. That's the point. It's okay? Is that okay? Thanks. Okay. So let me give you one example. Okay, let me go into one example which is not these stationary solutions. So for the example, I'm going to consider the three sphere with a round metric with constant sectional curvature 1, and then for any one parameter of these ansatz for the solution. This is just rescaling the metric by lambda t and rescaling the volume by eta t. Okay, this is going to be my ansatz for the solution of generalized Ricci flow. So with this ansatz, generalized Ricci flow implies that eta t equals to eta 0. So eta t is constant. This is not surprising because the generalized Ricci flow is preserving the cohomology class of the free form. Okay, and this is changing the cohomology class. So eta t needs to be constant. And then we reduce to an evolution equation for lambda, which reads as follows. The partial derivative of lambda with respect to t is -4 plus eta 0 squared divided by lambda squared. So there are two different cases. One case is when eta 0 is 0, and then we simply obtain partial t of lambda equals -4. So the solution to the flow exists in this interval and becomes degenerating infinite time. So this is just, in this case, where eta 0 equals to 0, this is just a solution of Ricci flow on the free sphere. Okay, so the solution of Ricci flow on the free sphere is given by lambda -4t times the round metric, and we have obtained something classical, which is that the round sphere shrinks homothetically at constant rate until the diameter goes to 0 infinite time. So what happens if eta 0 is non-zero? Well, if eta 0 is non-zero, then things become very different. So when the free form is present, there is a unique fixed point given by lambda equals to norm of eta 0 divided by 2. And this is an attractive point. Okay, so the solutions are going to have a partial derivative positive when they are on the left, and partial derivative in time negative when they are on the right. So you can show this is an exercise, or you can just go to the book and to check our proof that for any choice of lambda, the solution is going to exist for infinite time, and lambda t the fixed point for this ODE. Okay, so we see a striking difference between the case without form, so the case of the Ricci flow, and the case with the free form, with no matching free form, which is that in a sense the free form is going to attenuate the singular behavior of the flow. And more generally, in higher dimensions, what is going to happen is that whenever you have a non-zero free form and you evolve your metric by generalized Ricci flow, the directions of the manifold, the directions on the manifold which are detected by the free form are going to be prevented from creating singularities, are not going to shrink until to zero length in any finite time. Okay, so this is the example. And if there are no questions, are there any questions about this? So if there are no questions, let me go to formulate this conjecture that you can find also on the book, which is the following. Let me just state the conjecture and then explain you why the previous examples motivate this. So let G be a compact semi-simple Lie group with invariant metric G infinity. And we take any left invariant metric on the group and set H0 to be the Cartan free form with respect to this invariant metric. Then the conjecture is that the generalized Ricci flow with initial condition G0, H0 exists in infinite time and converges to the invariant metric and the Cartan free form. Okay. So let me give you examples. So for G equals SU2 with G0 equals lambda times G infinity. So when we have a multiple of the invariant metric, this corresponds precisely to the previous example. Okay, identifying SU2 with a 3-sphere. And now an exercise in ODE that you can do is to prove the conjecture for G equals SU2 and G0 not being a multiple of G infinity, but to be diagonal, a diagonal left invariant metric in an orthonormal basis for G infinity. And a spoiler is that this is written down quite explicitly in the book. Okay, so with this I finish this part. If there are no questions, let me go.
Could I ask about that?
More generalized geometry things. Are there any questions?
So in the case of for this
Yes.
for this
Sure.
example, what kind of ODE do you actually get? Is it something like a Riccati equation?
So you have 3 evolution equations for the 3 components, and yeah, I don't know if they look like Riccati. I don't know if Jeff.
But it's, I mean, you're getting a nonlinear ODE, right? Describing the evolution, and I'm just wondering if the right hand side is quadratic in the
Yeah, I guess it's always of the form. There's like a constant term and then a like inverse quadratic term, like in that example. Yeah.
I see. And I'm just wondering, like, because that looks to me like a Riccati equation, which typically, I mean, typically you will have like finite time singularities. So I'm just wondering what happens, like what is it that like, I mean, I understand that there's a priori reason to expect that the thing will not collapse, but I'm wondering from an ODE point of view, what happens that stops it from collapsing?
Well, I think it's just like on the, I mean, more or less in this simple example that Mario mentioned, it's basically, that's just what's happening, except it's on the level of the entire matrix now, instead of just, I mean, there he already did like multiples of the biinvariant metric, but somehow there's like, at the level of eigenvalues of the metric, it's the same kind of behavior happening. If it ever gets too low, then the h² term brings it up, basically. There's sort of a convexity principle.
Yeah, in case this helps, these are the coefficients of the metric in this SU2 example, and this, what you get is 1 over BC and then minus 4 a squared plus 4b minus c squared plus 1. And the other 2 equations are getting like just by cyclic permutations of this expression. I don't know if this helps.
Okay, thanks. Yeah, I'll have to take a look. It's written, this example is written in your book, right?
Yeah, this is example 4.2, example 4.15.
Okay, cool.
Okay, so let me go back to the.
No, actually, Mario, I
the
noticed
slides.
you're kind of at the
this
natural
other part,
breaking
part, which is
Yep. I mean, and it is close to 2. I do have something at 2. I mean, normally I don't, but and I'd be happy to go after. But maybe it seems like a natural place to stop as any. Or, is it okay with you? Or
yeah, sure,
maybe,
sure.
Maybe
I'm fine with that. Yeah, general geometry
maybe you could
part.
just say a little bit about
next
where
lecture.
the actual generalized part comes in, or just as a preview for next time. Or something.
Yeah, sure. Yeah. Yeah, I don't know if I can do it in the here. Or let me just show my slides. Maybe. Let me just comment briefly on this. Well, this is just the word is okay. Let me do it in the whiteboard. Otherwise, it's going to be messy because we're going to follow this thing. Okay, so the thing is the following. So we have these generalized Ricci flow equations, and they look a bit weird because they depend on this, or there are equations for a metric, a 2 form, and I'm choosing some closed 3 form on my manifold. So the question is, what are the symmetries of the equations? What are the symmetries of generalized Ricci flow? And motivated by this picture about 2-dimensional sigma models, what I'm going to explain next day is that there is some very natural geometry, which is a generalized geometry, which captures the natural symmetries of generalized Ricci flow. So more precisely, what is going to happen is that I'm going to consider some structure called current algebroid, exact current algebroid, which is constructed on the following bundle over the manifold, the tangent plus the cotangent bundle over the manifold. This structure has a natural pairing involved, which has a split signature and a bracket that I cook up out of this complex 3 form. Sorry, out of this closed 3 form. And now the automorphisms of this current algebroid are going to preserve the equation and are going to give us symmetries for these generalized Ricci flow equations. So the new component or the new ingredient in this automorphism group is that enlarges the diffeomorphism group of the manifold by the 2 forms, the space of 2 forms on the manifold acting by B-field symmetries. So here, if I have a 2 form on the manifold, then I can act on a section of this tangent plus cotangent bundle by doing x plus g plus ixb. And this is going to be this natural action of tangent plus cotangent. So just to finish, let me mention that out of this sort of simple remark that, or I don't know, this basic, it's not a simple observation, but it's a basic observation that the automorphism of an exact current algebroid preserve the generalized Ricci flow. Then we're going to obtain some spin-off applications. One is going to be natural notion of soliton for the generalized Ricci flow, which are supposed to be like the limits of generalized Ricci flow when t goes to plus infinity. We're going to obtain also gauge fixed versions of the flow, which are going to be used for the short time existence, even though we have a classical proof, but they can, at least this classical proof can be interpreted in these nice terms. The other thing we are going to obtain is that we obtain versions of generalized Ricci flow which are adapted to complex geometry. These are going to be the pluriclosed flow introduced by Street-Santian, and also the generalized scalar Ricci flow introduced by them as well. And finally, we are going to see that all these equations and geometric structures are compatible with a natural symmetrical T-duality. So this is going to be what is going to come about in the next days. Okay, so I finish here. Thank you for coming to the seminar and listening. Jeff ran away, so I maybe I'm in charge of
Sorry,
this.
sorry,
No,
I'm back.
Jeff is back.
There's like I'm in 2 Zoom meetings at once right now. But yeah. Sorry. Yeah. So maybe let's just thank Mario really quick. So yeah. So thanks, Mario.
Thanks.
And yeah. So hopefully it gives just a tiny taste of what the equation is, what it can do, and also there's just some teaser for like. I mean, I think probably there were some flow people here for whom this was really elementary, and maybe some generalized geometry people here for whom maybe, I don't know how it sounds, but they're going to get glued together. Hopefully the flow part will get less trivial and the generalized part will get more interesting soon. So basically the plan, at least for now, is, I mean, I guess, yeah, so Mario's going to introduce some basic aspects of generalized geometry motivated. I mean, anyway, so he'll talk about it next week, and then we're gonna sort of discuss the linkages between this subject I find very beautiful, this sort of generalized geometry, and actually do a little bit of analysis with it and stuff. So yeah, just one last time, yeah, please do email me if you are here and want to keep coming, and otherwise. I'll see you guys next Thursday, same time, same link, and we can be a bit more casual about letting it run over or whatever. That's all. Yeah, so
Okay.
Thanks again, everyone.
Thanks, Jeff. Bye.